Mm-hmm. Yeah, there'll be an email announcement. Okay, let's start today's lecture. You may notice a few things today. I don't have my laptop with me. I decided that old-fashioned technology is probably better for this class. So I'm going to be writing notes on paper. And a couple reasons for that. One, I don't think the notes come out very clear on the video. And two, I think I'm going too fast with the lecture slides. So if I have to write things down, at least that slows me down. Yes.
Will notes still be posted?
Yes. I still will have the typeset notes available. In fact, what I did was for the last couple lectures, we went off on a lot of tangents on paper. So I had those scanned in. Those are also available for the last two lectures. And from now on, you'll have both the notes that we write in class and the typeset notes. The other announcement I wanted to make was from some of the questions I got last lecture, it seemed like some of you needed a refresher on resonance and second-order circuits. So I posted a chapter from a book that I'm working on right now. First half of that book talks about the material that we discussed in last lecture, so it's a good review if you want to read that. The second half of that chapter is on matching networks, which we'll cover in probably 2 lectures from now. Okay. Last lecture, someone asked where do we turn in homework next week. As you know, I'm not going to be here next week. We're going to pre-tape the lectures tomorrow, starting at around 11, probably 11:15, and we're going to tape both lectures. So, highly encourage you guys to come in if you have the chance to come in tomorrow, and then you don't have to go to lecture next week. But to turn in the homework, you can turn it in class on Tuesday. I'll send my the reader in, and he'll collect the homework assignments. Okay. Any questions?
Just slide it under your office's
No, I
door?
prefer that you bring it in on even if you're not going to come into the lecture, just turn it in so they're all in one place. It's much better.
What time should we show up on Tuesday?
Regular time.
So at the beginning?
I asked him to come at the beginning, but he'll probably make 2 rounds. He'll come in at the end as well. Okay. If you can't find the reader for some reason, you can also turn in the homework on the 2nd floor of Corey to the administrative assistant, Rosita Alvarez. Okay. All right. Okay, so to the technical matter. So this lecture, we're going to talk about general properties of 2-port networks. And in other words, we're going to take our amplifier and treat it like a black box. So for instance, we're going to hook up a source resistance, say ZS, source impedance, more generally VS, and we're also going to connect a load, let's say ZL. And we want to know what are the general properties of this 2-port. Now, as you know, we can describe a 2-port in terms of its 2-port parameters. So for instance, if I pick Z parameters, I can completely describe this 2-port by Z11, Z12, Z21, Z22. So we're going to review how we calculate these 2-port parameters, when we use them, when we don't use them, and what kind of information, what kind of conclusions we can draw from basically just studying an arbitrary 2-port. And in fact, you'll see that we can draw a lot of conclusions about an arbitrary 2-port that we can apply to real circuits. So now you might ask, well, what's inside of this 2-port? Well, anything can be inside this 2-port. It can be anything as simple as a transistor, right? If I take a common terminal, 3-terminal device with a common terminal, that's a 2-port, right? It could be a 2-stage amplifier, let's say. Even, let's say, with a load resistance. So this is power, ground, and we're only interested in the AC port. So we ignore the power and the ground, and this is the input port, and this is the output port. So we can draw a box around this entire 2-stage amplifier. Okay. Now, there are several different kinds of two-port parameters that we can define. For instance, Z parameters describe the relationship between voltages and currents. And if this matrix is non-singular, we can also invert it, or in other words, use Y parameters. And we don't necessarily just have to use voltages on one side and currents on the other side. I can use, let's say, input voltages and input voltage, input current, output voltage, output current, or any combination thereof. So basically I have V1, V2, I1, I2. I can choose any two of these and write them as a linear function of the other two variables, because only two variables here are linearly independent. So I have Z parameters, I have Y parameters, I also have H parameters, which are the hybrid parameters, and I have G parameters, which are the inverse hybrid parameters. Okay, and they're all equivalent. They really are all the same equivalent information. So in general, we use the ones that are most convenient for the problem we're solving. You should also note that not all of them necessarily exist. So for instance, you can dream up of a circuit that has Z parameters that does not necessarily have Y parameters. That's because we can't invert these relationships. Now, the way we determine the most convenient parameters to use is really determined oftentimes by the type of feedback we use. So for instance, if I have a two-port and I connect another two-port in parallel, as so, and I want to calculate the overall Y parameters, let's call this Y1 and this Y2, where these are the two-port matrices, 2 by 2 matrices. The overall Y parameter, of course, is Y1 plus Y2. And that's because the voltages are actually the same. In other words, I have V1, V2 is Y111, Y11, Y121, Y211, Y221 times I1, I2, and you can see that this is I1, 1, this is I1, 2, and you can see that I need to sum the currents, and the voltages are the same. So when I sum the currents, I end up summing the Y parameters. Now, is there a question? Oh, thanks. Thank you. So, in a like manner, if I were to connect these two ports in series, then I would sum Z parameters. And if I take the input in series and the output in shunt, or vice versa, I use the G or H parameters. Okay. Now, let's also review, let's focus in on Y parameters, also called the admittance parameters. So for the admittance parameters, I have V1 is Y11 I1, Y11 V1 plus Y12 V2. And you notice that if I short circuit V2, if I set this equal to 0, then Y11 is simply I1 over V1 when V2 is equal to 0. Likewise, I2 is Y21 V1 plus Y22 V2. Again, I've shorted this out, so Y21 is I2 over V1 for V2 equals 0. And in the same very identical way, by shorting port 1, I can calculate Y22 and Y12. Okay. Now, an important concept is a unilateral two-port. And the way we usually draw a unilateral two-port is instead of a box with a triangle. And we define a unilateral two-port as one where Y12 is equal to 0. Or equivalently, if we're using Z parameters, Z12 would be equal to 0. Or H12 would be equal to 0. Or G12 would be equal to 0. And the reason we do that is, if we look at our equations, we can see that the input current, if Y12 is equal to 0, is simply a function of the input voltage, and the output current, on the other hand, is a function. In other words, the input can influence the output, but the output can't influence the input. So in this equation here, we see that the output doesn't influence the input current. And that's why we call it a unilateral device. The triangle points in the direction of influence, right? Input signal here produces output signal here. Output signal here does not influence the input signal. And of course, when we design amplifiers, we like them to be unilateral. Now, for any real device that you design, physically it's not going to be unilateral. Y12 can never exactly equal to 0. You can make it very small, and in this class we'll figure out how small we need to make it in order to make things stable, as we'll see later on. Y12, again, let's take our example of a transistor. We know that a transistor would be unilateral if C mu did not exist. So C mu makes our device bilateral. And what we'll find out is that not only is C mu bad for bandwidth for, let's say, a common source amplifier, but the fact that we have C mu means at high frequencies we have feedback. And this feedback is dangerous because we know from 140 that feedback produces stability problems at high frequencies. Okay. We'll have a lot more to say about that as we go forward. Well, let's look at the Y parameters of a simple transistor model. Let's say a FET or a BJT, it doesn't really matter. So I'll do a BJT just so it's clear. So our small signal equivalent circuit looks something like this. Where this is R in, this is C in, voltage across here is V in. This current here is GM times V in. This is the R out of the device, this is the output capacitance of the device, and of course this is C mu of the device. And this is the input port, let's say, and this is the output port. So this is a common source configuration. Well, let's call this Y mu. Let's call this Y pi, and call this Y0, or Y out. In other words, the equivalent circuit in terms of admittances is a pi circuit. This is also why we like to call this hybrid pi models. And you'll notice here that V1 is actually the same as V in. So I can just write GM times V1. Okay? So now, in order to find, let's say, Y11 for this circuit, remember we take the output and we short circuit it. So V2 is equal to 0. And that means all the current of this generator here will flow into I2. In other words, if I now connect the voltage source here, V1, I'd like to know the current I1 And you can see now that Y11, which is the input admittance looking into here with a short circuit at the output, is simply Y pi plus Y mu, because this is shorted. These are in parallel, so admittances in parallel simply add. On the other hand, Y21, which is really the current I2 due to V1, is now simply going to be the sum of the current GMV1 minus the current flowing through here. So Y21, which is I2 over V1, for V2 is equal to 0, is GMV1, so I divide by V1, minus Y mu. Okay. Now if I do the same calculation at the output, I short the input, calculate the output admittance. First of all, notice that I don't need to include this current generator because V1 is shorted. So this is I1, this is V1 equals to 0. And because I've shorted this out, I can also forget about Y pi. It plays no role. So I simply have Y mu and YO, and from port 2, if I look in, that's Y22. So Y22 is simply YO plus Y mu, and Y12, which remember is the feedback, it's the element that makes our device non-unilateral, is the current I1 due to applying a voltage V2 here. And you can see that that current is just minus the current that's flowing V2 Y mu. So it's minus Y mu. So I have it. I have the Y parameters of my transistor. Y11 is the input admittance. It's related to Y pi and Y mu. Y21 is related to the transconductance of the device. And you can see that the effect of C mu in this device is that it reduces the transconductance, effectively reduces the transconductance of the device. At low frequencies that we're used to dealing with, GM is much larger than J omega C mu, so we can neglect this term. Output impedance is the output impedance due to RO, CO, and C mu, and Y12 is simply the parasitic feedback of the device. Okay, questions? All right, so you may ask, why are we using two-port parameters? You know, why not just do small signal analysis of various amplifiers and be happy? Why are we looking at a transistor or as an amplifier as a black box? What kinds of advantages do we get? Well, first of all, the two-port parameters are generic. And they're independent of the details of the amplifier. In other words, just as we saw, it could be a single transistor or it could be a very complicated multi-stage amplifier. The other reason we use two-port parameters is that we'll find that at high frequencies, transistors in particular are more easily described with two-port parameters. And this is due to the distributed nature of the input gate and the channel. In other words, as we alluded to in the first couple lectures, the equivalent circuit that we have for a transistor really only works at really low frequencies. If you go to really high frequencies, the model breaks down. And if you want to model the transistor at really high frequencies, it turns out, especially as the device becomes more distributed, it starts acting more like a transmission line. It's very difficult to write equations for that. You have partial differential equations. But you can always simplify that complicated transistor structure into 4 Y parameters. So even at really high frequencies where distributed effects have taken over, we can still have a pretty good idea of what's going on if we use Y parameters. Okay. The other advantage of using 2-port parameters is that feedback amplifiers can be often decomposed into two 2-ports. A 2-port that accounts for the amplifier and another 2-port that accounts for the feedback. And as we know from feedback theory, we'd like to compose it into a mostly unilateral forward amplifier and a feedback network. Okay. And then finally, probably one of the most important reasons for doing this is that we can make some very general conclusions about 2-port power gain that apply to any amplifier that you can design. So we can make some very general conclusions about quote-unquote optimal power gains of a 2-port. And in fact, it turns out that when we go through these calculations, a lot of the metrics that we define for transistors, such as Ft, which you're familiar with, and Fmax, which is something that some of you are familiar with. Fmax is known as the maximum frequency of oscillation for a transistor, or in general we'll see for a 2-port, really come from these kinds of detailed studies of the properties of 2-port networks. Okay. Questions? Comments? All right. Let's look at something simple like voltage gain. So, what's the voltage gain of a general 2-port? Let's hook up a YL and drive it with YS. And let's call this I want to drive it with since I'm finding voltage gain, I'm going to drive it with a voltage source like this. Okay? So if I observe that I2 is simply minus V2 YL, and I substitute that into the equation, my equation is that I2 is Y21 V1 plus Y22 V2, and that's equal to minus V2 YL. Then I can write that Y22 plus YL V2 is minus Y21 V1. In other words, the voltage gain in terms of V1 and V2, remember this is V1, this is V2, is simply minus Y21 over Y22 plus YL. Okay? And that's actually quite a trivial result. If you check it for a transistor at low frequency, Y21 is approximately GM, and Y22 plus YL inverse is simply RO in parallel with RL. So the voltage gain is, as you know, minus GM times RO in parallel with RL at low frequencies. So that matches with our previous knowledge. How about the input impedance of a two-port? So let's calculate the input admittance. Okay. Yes, question? Sorry, I should have drawn a bigger picture here. Any questions about that? Okay. Is it okay if I move it away now? All right. So how about the input impedance? So the input impedance, this time I'll draw a better picture. I have YL here, and I simply want to know what Yin is. And this is an arbitrary two-port. Now remember, if I short circuit the output, Yin is just Y11. But I want to find it under general conditions. So under general conditions, this is V1, and this is I1. So Yin is simply I1 over V1. Okay. So I1 is Y11 V1 plus Y12 V2. So Yin is Y11 plus Y12 V2 over V1. And I just calculated what the ratio, remember V2 over V1 is Y21 YL plus Y22. So the input admittance is Y11 minus Y12 Y21 YL plus Y22. Now this is a very important equation. I think you'll encounter it enough that you'll begin to find that you've committed it to memory. And there's a couple of interesting things in this equation. First of all, if you have a unilateral amplifier, let's just say unilateral two-port to be more general, then Y12 is equal to 0. And if I substitute Y12 equal to 0, then Yin is simply Y11. Which makes sense because, again, the output of a unilateral two-port can't influence the input, so the input admittance has to just be Y11, independent of the output. Okay. On the other hand, if Y12 is not equal to 0, we can see the input admittance is a function of the load. In other words, if somebody tells you what's the input impedance of a transistor and they don't specify the load, then they haven't specified completely, they haven't really asked a good question. They have to tell you what's the input admittance either under a short circuit load or open circuit load or a given load impedance. And as I talked about last lecture, we talked about designing a tuned amplifier. And I mentioned that unless the amplifier is unilateral, it's pretty difficult to tune the input and output together. And the reason for that is really comes from this equation, because let's say I have an amplifier and I want to tune the input and output together. So let's say I first select L to resonate with this capacitor and the device capacitance. But because I have C mu, what value of L I pick also depends on what value of L I pick on the input. Let's call this L1, let's call this L2. So if I want to, let's say I want to match L1. I want to find L1 to resonate out with the input admittance. But the input admittance is a function of YL, and YL includes this L2 that I've added. So you can see that if I want to find what L1 to choose, it really depends on what L2 I need to choose. And to choose L2, I need to know L1. So the only way around that is to solve two equations simultaneously. In fact, by symmetry, Y out for the two-port is given by the same exact equation. The Y out for a two-port is simply, we just change 1's to 2's. And YL becomes YS, and Y22 becomes Y1. So in general, for any two-port, we can see that the output admittance depends on the source admittance, and the input admittance depends on the load admittance. Okay. Questions? Okay, so we found the voltage gain for the internal nodes. Let's find the so-called external voltage gain. In other words, from the source to the load. So let me redraw the picture. So in this case, V2 is equal to VL, the load, but V1 is not equal to Vs because of some finite source admittance here. Okay? So what I'd like to find is the voltage gain V2 over Vs. And I can write this as V2 over V1 times V1 over Vs. Okay. Now V2 over V1, we already found that, and let's just call that AV. So what I really need to do is just find V1 over Vs. That's easy. That's just a voltage divider. So what I have is AV times the voltage divider Zin divided by Zin plus Zs, which is Ys over Ys plus Yin. And remember, I've calculated Yin before, so I can substitute for that. But before I do that, let me just substitute for AV. AV we found to be Y21 over Y22 plus YL. This is Ys plus Yin, and this is Ys. So all I need to do here is substitute for Yin from the equation that I found. And if I do that, I get minus Ys, Y21, Y22 plus YL, Ys plus Y11 minus Y12, Y21 divided by YL plus Y22. Now if I multiply this out, I get minus Ys, Y21. So let me multiply this in, rather. You can see that this and this factor here cancel out. The first factor is Y22 YL times Ys Y11 minus Y12 Y21. Question?
So the devices that we model with two-port network should be linear, or they could be any?
Yeah, that's actually a very good point. Two-port analysis is only valid for linear circuits. In other words, we said that V1 and V2 is a linear function of I1, I2. That's only true for a strictly linear system. So if you have a nonlinear circuit, you have to linearize about an operating point. And once you linearize about the operating point, then the representation is only valid for small signals. Okay, good question. Okay, so this equation here, let's also substitute what this equation reduces to at low frequencies for, let's say, a FET. So let's take AV prime at DC. Ys is Ys. Y21 will just become G1. And at low frequencies in particular, Y12 is equal to 0, right? So y12 is minus j omega c mu, and so at low frequencies this term goes away. So we just have y22 plus yl, y11 plus ys, and if I substitute, this is basically 1 over rs, this is gm, this is times 1 over y22 plus yl, just like before, is RL in parallel with RO, and this, let me rewrite this in a slightly different way. If I divide everything out here, this ys over y11 plus ys is simply zin divided by zin plus zs. So of course this is a trivial result again, so let me take this out. This is just telling us that at low frequency the gain is gm minus gm times RO in parallel with RL times some voltage divider. That's trivial. Okay. Another thing that we can do with y parameters in particular, and actually it turns out, let me say something that's interesting. All the equations that we've derived so far are also true for z parameters. In fact, a lot of the equations that we derive in this class are exactly the same for h and g parameters as well. In other words, this equation, voltage gain, minus y21 over y22 plus yl, also holds for z parameters, also holds for h parameters. So it's very convenient. If you derive the equations once for one set of parameters, you can reuse them again and again. In particular, let's look at feedback. Now, we use y parameters when we use shunt feedback. So in particular, the example, the first homework problem that you guys worked on can be really nicely attacked using y parameters. Okay? So we know that in a feedback system, if we have a unilateral amplifier and then we have feedback, then we know that the closed loop gain of a feedback system is simply A over 1 plus AF, where A is the unilateral forward gain and F is the feedback factor. Now let's look at this expression that we derived for the voltage gain. We derived an expression for the voltage gain of a two-port. It's an arbitrary two-port, so certainly can be a two-port that has feedback in it. And we notice that if we define an AVU, in other words, the same voltage gain where the device has been unilateralized, that's equal to AV prime for y12 is equal to 0. So it's simply minus ys y21 divided by ys plus y11 yl plus y22. So we could call this the unilateralized forward gain of the amplifier. In other words, we've removed the feedback because we've removed y12, and this is the forward gain that we get. Now if we go back to the expression for AV prime, let me see if I could fit that in there. Let me divide this expression by this term. And easier done than said, so let me just do it instead of saying it. So this term here becomes 1, because that's the term I'm dividing by, and this term is y21 divided by ys plus y11 yl plus y22. Okay? And then we stare at this for a while. And we say, wait a minute, this term here is exactly AVU. So I substitute AVU. And this term here, therefore, must be the loop gain. In other words, the loop gain of this feedback system is AV, which is AVU times F, is minus Y21, Y12 divided by YS plus Y11 and YL plus Y22. So I encourage you to take the first homework assignment, if you have some free time, apply this two-port analysis to it, and you'll see a very easy way to calculate the loop gain. So if this is the loop gain, and the loop gain is equal to AVU times F, we can also solve for F, which is Y12 over YS. And now if we look back at our expression for the input admittance, right, we derive that in general the input admittance is Y11 plus YS minus Y12, Y21 divided by YL plus Y22. If I factor this first term out, I have Y11 plus YS times 1 minus Y12, Y21, YL plus Y22, Y11 plus YS. And if I look at this expression here, I can see that that's actually equal to my loop gain. In other words, I've just shown that Yin is Y11 plus YS times 1 plus T. In other words, the action of the feedback is to increase the input admittance by a factor of T, 1 plus T. So now you can see that the input admittance without feedback is simply Y11 plus YS. Application of feedback raises the input impedance by the loop gain. By symmetry, the same exact argument holds for the load. We can see that shunt feedback now increases the output admittance also by a factor of 1 plus T. And we know that to be true in general of shunt feedback. Now what's interesting is these same formulas apply exactly for Z parameters. And we know that Z parameters represent, if I look at Z12, that represents series feedback. So if the same exact formulas hold for Z parameters, the same equation tells me that the input impedance is the input impedance without feedback plus 1 plus the loop gain. In other words, series feedback raises the input impedance and raises the output impedance. And if I use some hybrid parameters, let's say I have series feedback on the input and shunt feedback on the output, then this part would represent the increased input impedance due to the series connection, and this part would represent the increase in the admittance due to the shunt connection. Okay? All right. Any questions up to here? Comments? Yes, Kevin.
So for AV, why are we using Y11 instead of YN?
We're
Page.
previous
Or-
page. Okay. This equation
Yeah.
for AV.
Mhm.
Where are you referring to?
The top is this because you divided by AB, right?
No, all I did was going back here. So this is the expression for AV prime, right? I'm going to divide by this term here. Okay? It's just a simple mathematical transformation. So if I divide the numerator and denominator by this term, this is what I get.
Right. So in A prime V, why are we using Y11 instead of YN?
Okay, I still don't know.
Oh, never mind. I'll figure it out.
Okay. Yeah, maybe I made an algebra mistake. Sorry, I had enough. Did anyone catch that? Okay. Yeah, maybe we could look at it after class. Maybe I made a mistake. All right, any other questions that I might be able to answer? Okay, you guys are quiet today. All right, so up to here it's been pretty simple. Now we're going to start to look at power gain. And several lectures back, I made the claim that power is more important than voltage gain or current gain, especially in RF systems. So when you come to define power gain, you run into a little bit of problem. You basically have to specify what you exactly mean by power gain. And it turns out that we can define several different types of power gain. So let's work, for instance, with this setup. This is our generic 2-port. Let's define P in as the power going into our 2-port. Okay? And let's define PL as the power flowing into the load. Turns out that it's very interesting to also consider the power that's available from the source and the power that's available from the 2-port or the load. Okay, so what do we mean by available power? Okay. Okay, anybody? What is the available power? Okay, so the available power is the maximum power that you can extract from a source under matched conditions. Okay, there's a question. Can you use the microphone?
What are the two P's on the bottom again?
Yeah, this is what we're discussing. These are the available powers. So the available power from the source is the maximum power that I can get from this voltage source. Now, because this voltage source has source admittance, the maximum power I can get out of it is not infinity, right? If this were a short, I can get infinite power out of this voltage source. Any real voltage source we know has some source admittance, so I can only get a finite amount of power from it. So the question is, what's the maximum power that I can extract from this source? Well, you all know the answer. We talked about it last lecture. That's given to you by the power transfer theorem, which says the best power that you can get from this source is the power you get when you conjugate match this source. In other words, if I connect YS star, I then can extract the maximum power from this source. Okay? Likewise, power available at the load is the maximum power that you can extract from this 2-port. Okay? So you might ask, why are these interesting? We'll come back to that. We'll define a gain called the transducer gain, which is a very interesting comparison. Okay, so let's first of all define what the normal way any of us would define power gain in the following way. So we're going to define GP as the power gain as simply the power that goes to the load divided by the input power, right? That seems like a logical calculation. This is the power going to the load divided by the power going into our network. Okay? And the power that goes into our load, you can see, is a function of what load admittance we choose, right? And it's also a function of the 2-port parameters of our network. But what's important is it's not a function of the source admittance. In other words, we've normalized already by P in, so now, no matter what source admittance we choose, it won't affect the power gain because we divide by how much power that goes in. If I use, 1 ohm or 1,000 ohms, I'm going to get some power in. They're going to be different, but then I divide by that power in, so that the power gain, GP, is not a function of the source admittance. Well, that's an observation that we need to keep in mind. Okay. Another way we can define power gain is the available power gain. So the available power gain, GA, is the power that's available at the load divided by the available power at the source. So it's something like saying, okay, I know I have a certain source impedance. I have a certain source which has a certain source admittance, and that has a certain available power. I know the most power I can extract from it is this. Now I put in a 2-port. How does that 2-port change things? Does it make the available power larger? How much larger? So this is a comparison of how much power I can extract from my 2-port optimally versus how much power I can extract from my load. Okay, and we call that the available power gain. Now what is this going to be a function of? Any guesses? Someone want to use the mic if they have a guess?
Function of ys and yij, but not a function of yl.
Exactly, right? Because we're not actually talking about how much power that goes to the load. We're just looking at how much power we can extract from the 2-port. Very good. So this is a function of ys because the power available from the source is a strong function of ys. It's a function of our 2-port, but it's not a function of the load. Okay? Questions? All right. Finally, let's define the transducer gain. The transducer gain is an interesting one. It's the power that goes to the load divided by the available power from the source. In other words, transducer gain tells you how much better you're doing than a matched load, right? What does that mean? So if I come here and I just, instead of putting in this 2-port, if I just connect my load and I make my load complex conjugate of ys, I'll extract power available from the source, right? I'll extract this quantity, which is the power that's available from the source. Now I compare that to how much power is actually going to the load. And so this transducer gain tells me how much better I'm doing normalized to a simple termination, right? In other words, if my transducer gain comes out to be less than 1, this 2-port's not providing any useful power gain. It's actually doing worse than you would if you just simply matched the load. Okay? So what is this going to be a function of? Anybody? So is it a function of the source impedance? Certainly, right? Because its source impedance tells us how much power is available from the load. Is it a function of the load impedance? Yes, because that changes how much power goes to the load. In other words, unlike the previous two quantities that we've defined, this is both a function of the source impedance, the load impedance, and the 2-port parameters. Okay. Questions? Okay. Now, we can calculate some of these quantities in terms of y parameters. The power going into the network is simply the real part of V1 times I1 conjugate divided by 2. And I can write that as the real part of V1. I1 I can write as Y conjugate V1 conjugate divided by 2. And this simply is V1 squared divided by 2 times the real part of Yn, because the real part of Yn is equal to the real part of Yn star. So similarly, the power going to the load is V2 squared divided by 2 times the real part of YL. So the power gain, which is simply PL divided by Pin, is the voltage gain squared times the real part of YL divided by the real part of Yn. And if I substitute for the voltage gain, it's the voltage gain squared, magnitude voltage gain squared. Well, I found that the voltage gain was Y21 divided by YL plus Y22 squared times the real part of YL divided by the real part of Yn. And of course I can now substitute for y in terms of the y parameters. And question?
Why are you using the conjugate when you're multiplying the voltage and the current?
So this is the definition of power. So if I want to know the power flowing into a port, the real power, I can take the voltage times the current conjugate, or I could take the current times the voltage conjugate, and take the real part, and 1/2. That represents the real power flowing into a 2-port. Okay, you should review that. That's kind of EX 40 material. When you have a current and voltage and they're out of phase, this is what you get. Yeah, so review that result. Yes, question?
Does this assume a matched load condition in the input when you are considering P in?
No, right? Because we just use a general expression for I1. I1 is the current going into a 2-port. The current going into a 2-port is Y in. So we haven't assumed anything about matching. Okay, and just as we guessed, if I look at this equation, Y in is a function of YL, right? Because it's not a unilateral device. And otherwise, I only see YL and the Y parameters of the device. So we were correct in assuming that GP is only a function of YL. All right, let's also derive the available gain. To derive the available gain, I need to find available power from the source. That's trivial. What I need to know is the available power from a 2-port. So to do that, I'm going to transform my 2-port into an equivalent Norton source. So I want to transform this general 2-port and looking at it from the outside, I want this to be basically some I equivalent and some Y equivalent. Because if I do that, then I know the available power from this source trivially. I can just calculate it by hand. Okay. So to find I equivalent, I note that if I connect the short across here, all the current flows through that short. So if I short this port as well, so I'm going to connect the short here, and observe the current I2, that current I2 will be minus I equivalent. I'm just noticing a sign error in my notes. So let's calculate. So I'm going to say that I2 is minus I equivalent, and I2 is simply Y21 times V1, because V22 is equal to 0. V2 is equal to 0. And basically V1, if I come back and look at this, if I short circuit the output port, the input impedance is just Y11. So V1 is simply IS times this input impedance, which is 1 over Y11 plus YS. That makes sense? In other words, I equivalent is minus Y21, Y11 plus YS. There should be a minus sign here. Okay, and then Y equivalent is simply the admittance looking into here. So we've already calculated that. There's no need to recalculate it. That's simply Y22 minus Y12, Y21 divided by ys plus y11. Okay, so now that I have the equivalent circuit here, I know what the available power is from this network, so I can write down the available power gain. Well, the available power from the source is is squared divided by real part of ys. The available power at the load is I equivalent squared divided by 8 times the real part of y equivalent. And now if I take the ratio of the available power, I get basically this term here, which tells me the ratio of I equivalent to is. That's y21 squared, y11 plus ys squared, times the real part of ys divided by the real part of y equivalent. Okay, that makes sense to everybody? And of course I could substitute for y equivalent from here. And now if I observe the available power gain, I can see that it's certainly a function of ys. And if I look at y equivalent, it's only a function of ys and the y parameters of our device. So certainly this is only a function of ys, as we found previously. Okay. Questions? Comments? All right. So now let's calculate the transducer gain. So the transducer gain, remember, is the power that goes to the load divided by how much power is available from our source. And in case you guys are getting sleepy at this point, this stuff is actually useful. Lots of definitions, but we're going to make good use of it, hopefully by the end of this lecture, if not next lecture. So now the power available at the load is simply 1/2 the real part of the load admittance times V2 squared. Power available from the source is is squared divided by 8 times the real part of ys. And so I can rewrite this. 8 divided by 2 is 4. Real part of yl, real part of ys, times V2 over is squared. And I know V2 over V1. I've calculated that already. That's y21 over yl plus y22. And I know that is is basically V1 times ys plus yin in general. So I could write V2 over is as V2 over V1 times V1 over is. And that's going to give me y21 yl plus y22. And V1 over is is simply 1 over ys plus yin. Okay. And ys plus yin is simply ys plus y11 minus y12 y21 yl plus y22. As I said before, the formula for y in and y out will be committed to your memory very shortly. So now V2 over is, if I substitute from this equation, is y21 squared divided by ys plus y11 yl plus y22 minus y12 y21 whole thing squared. And that means that if I write the transducer gain, now using this, it's the same expression just multiplied by real part of yl, real part of ys, y21 squared, divided by ys plus y11, yl plus y22, minus y12, y21. Okay, big equation, If you didn't follow the derivation, it's very easy to derive it, so you can just look at it at home. Again, you can see that the transducer gain is a function of the load, source, and the y parameter. So just as we guessed before, this is a function of YL, YS, and YIJ. And remember, transducer gain is particularly interesting because it compares how well our two-port is doing compared to just a conjugate load. Now, it occurs to me that I probably didn't really motivate this topic properly. So let me try to now motivate this topic after boring you guys to death. Okay, so here's the motivation. I have a two-port. And I want to extract the most power I can. I want to basically find the optimal power gain that I can get from this two-port. And let's say this two-port has some certain y parameters, right? And these y parameters are fixed at a given frequency. Once I pick the operating point of this and I pick the frequency, the y parameters are just 4 numbers, right? There's 4 complex numbers. Now, to get the maximum power gain out of this, I notice that I can connect a load and a source. And in fact, I can vary my source impedance and load impedance in order to try to get the maximum power gain out of this two-port. You might say, wait a minute, you can't just arbitrarily change the source impedance and load impedance. Maybe you have some flexibility over this, but isn't this fixed? Well, it turns out that I can arbitrarily change it with matching networks. So we call this M1 and this M2. And this matching network, what it does is it takes my YS and converts it into YS prime, and it takes my YL and converts it into YL prime. And I can design, as we'll learn in the next lecture, I can design these matching networks to virtually synthesize any source admittance I want and any load admittance I want. So it is, in fact, as a circuit designer, once I've picked my transistor, I can pick my source and load admittance optimally in order to get the maximum power gain. Now, if I can find out that there is a certain optimal load and source, then I can synthesize matching networks that convert the real source and the real load impedance into those optimal impedances. Okay, is that clear? Now, if that's not clear, think back to the maximum power transfer theorem. Maximum power transfer theorem says I can vary my load so that I get the maximum power into this load. And we all know that that happens, let's say YL opt is equal to YS complex conjugate. So if I had just the load and I didn't have a two-port, then I would always pick my load to be the conjugate of the source, and that would transfer the maximum power into my load. Now I have a two-port, and I want to find the optimal load and source impedance in order to transfer the maximum power to the load. Now we're going to derive the optimal conditions very carefully using several different techniques, but it really doesn't take that much mathematics to understand what the right answer is going to be. Now, let me ask somebody who doesn't know the right answer who wants to guess, because I know some of you know the right answer and you can make it very trivial, but let's see if someone can guess what the optimum source and load impedance should be in order to get the optimal power gain from this two-port. So again, if you don't know the answer and you want to guess, go for it. If you do know the answer, keep it to yourself for now. Okay. Well, let me again make a strong analogy to this case. Right? In this case, we complex conjugate matched. And that transferred the most power into this load. Now, if I look at this load here, if I look back to the source, look back to the two-port, I can think of this two-port as all being this equivalent circuit, right? In which case, I would want my load to be the complex conjugate of the output impedance of this two-port, right? But the output impedance of this two-port is a function of the source. Likewise, if I want to transfer the most power into this two-port, I'd like the input admittance to be the complex conjugate of the source admittance. But the source input admittance is a function of also the load. In other words, I somehow want to do a simultaneous conjugate match, also called the biconjugate match, in order to maximize the power gain of this device. Okay? Now, if that's not clear, we'll do it the long way. Okay? So let's make some observations. So let's compare the various power gains that we've defined. Okay, so we know that in general, whatever power that we are able to deliver the load is less than or equal to the power available at the 2-port, right? And equality happens when we match Now by match, I mean complex conjugate match, right? Does this statement make sense to everybody? If not, let's back up and make sure that everybody understands the statement. Okay? Okay, we'll back up. So remember, PAVL is the power available from the 2-port. It's the most power you could possibly extract from the 2-port. And when does that happen? That happens when you put a load whose impedance is the complex conjugate of the output impedance of the 2-port. So in other words, for any other load impedance or admittance, I'll say them freely, and as we learned last lecture, we can do that, the power going to the load is always going to be less than the power available from the load, from the 2-port. Okay? That means that the transducer gain, so let's review. Transducer gain is the power of the load divided by the power available from the source. The available gain is the power available at the load divided by the power available at the source. In other words, GT is always less than or equal to GA. And in fact, so GT is a function of YS, YL, and it's always equal to less than or equal to GA, right? And if we go back, we can see that GA is only a function of the source, right? So this tells me that if I want to obtain equality, in other words, let's call it GT max source load, excuse me. If I want to obtain equality, I should choose YL is equal to Yout conjugate. That makes sense to everybody? So what I've done here is I show that the transducer gain is a function of two variables. And no matter what source and load I pick, I'm always going to be less than the available gain, which is just a function of the source. But if I just vary my load, if I make it just right, I maximize the transducer gain with respect to this variable. And that happens when my load is exactly equal to the complex conjugate of my 2-port network, output impedance, admittance. Okay. Clear? All right, not a difficult concept, but does take a little while to sink in. So, again, review it if it doesn't make sense offline, and please come to office hours if you have questions. Okay, so just as we could conclude that the load power is always available than the available power, then clearly the input power is always less than equal to the power available from the source, right? Because the power available from the source only occurs for a matched load. So equality again occurs for a matched source. In other words, when the source admittance is equal to the complex conjugate of the input admittance, then we have equality. Okay? So now, if we look at the transducer gain is PL divided by PAVS. If we look at the power gain we defined as PL over Pin. Right? Since Pn is always less than PAVS, we find that again GT, which is a function of Ys and Yl, is always less than GP, which is just a function of Yl. Okay, question?
I just didn't understand that that P in, that's the power that's flowing into the two-port network, and P available is the max power that I can draw from the source.
Yes.
So even if I am drawing means P in, how can it be equal to P is available S? Even under matched condition, some power will be dissipated in that source resistance.
Okay, by definition, P available is the power that you can extract, already taking into account the power you lose from the source impedance. Okay? Let me back up here and review available power. So I think there might be some confusion over the notation of available power. Okay, so let's say I have a source ZS and I want to extract available power, right? So I connect ZL equal to ZS conjugate. That means that my circuit simplifies into real part of ZS and real part of ZL because the imaginary parts just cancel each other out. So now I can calculate the current. Let's say I1 is Vs divided by 2 real part Zs, right? Because this is also equal to real part of Zs under matched conditions. And let's say V1, let's call this V1, is equal to ZL divided by ZL plus Zs times Vs, right? Just a voltage divider. And ZL plus Zs again reduces to twice the real part of Zs times Vs. Okay? Clear? So now to find the power that's dissipated in the input, so the power that goes in, Pin, which is also PAVS, is equal to 1/2 I1 times V1 conjugate. So that gives me Vs over 2 real part of Zs times ZL times 2 real part of Zs conjugate Vs conjugate. So this is Vs squared times 4 real part of Zs times ZL conjugate is the same as Zs conjugate. And I need to take the real part of this whole expression. So I forgot to do that. Oops, other way around. Kind of hard to draw backwards. There we go. Okay, and if I take the real part of this, and I also take into account this extra factor of 2 that I forgot, then I get Vs squared, and this is squared, which I also forgot to square, times 8, and then this is all real, so then I just take the real part of this, and so I get real part Zs squared times the real part Zs star, which is the same thing, and that goes away. So the available power from the source is Vs squared divided by 8 times real part of Zs squared. Okay? Alright, so next lecture, which will be tomorrow, we'll take the machinery that we've built up this lecture and we'll make good use of it.